So welcome to everyone, and we'll start with the news. And I have a nice laundry list. It's not just one bullet item of news, it's a list of news items.
Yeah.
And if you noted in the email, I actually gave you a hyperlink for each one of the news items. I actually pulled up multiple sources and then found the one that, first of all, didn't require a subscription. Second of all, didn't put a giant ad banner in front of you that you had to click through, and seemed to contain, you know, a relatively sane rather than media hype or fear and mongering content in it. So the first item is the Ingenuity Helicopter. They were up in the air about whether they were going to fly it again, or, you know, the original mission was, it's a demonstrator. It has demonstrated, it's done its technical thing. Yep, we'll fly one again in the future. And then they were going to park it over in the corner and never touch it again. But somebody said, you know, it can fly ahead of the rover, and it has a high resolution camera on the bottom, so it can give us a better view of where the rover is planning to go. So they said, okay, that's a good idea. So they're going to try that out within the next couple of days to have Ingenuity fly out along the path that Perseverance is going to be taking. So that'll be interesting. Next up is, as we mentioned a couple of months ago, China sent a probe to Mars, which had an orbiter and lander and rover attached to the lander. And the rover and lander did land on Mars successfully. And the rover has backed down off the top of the lander, kind of the same manner that the Sojourner rover did back when we had our first rover on Mars. It sort of drove itself down off the platform, and it went back and took a picture of the platform. Hi, this is where I came from. So that's going on. I'm not going to attempt to pronounce the rover name or the orbiter name, but in tonight's presentation, there's a separate slide just on that. So we'll cover that in a little more detail later. Apparently, there's going to be a lot of stuff going to the moon. And if you have that much stuff hanging out at the moon or landing on the moon, you need better communication, sort of moon ground to orbiter, and you need more precise location tracking of where you are on the moon. So the European Space Agency, ESA, is going to be deploying a moon GPS system. And also they're going to be putting in a moon high-speed network. I don't know how they're going to do the high-speed networking. I'm going to guess that it's going to be some orbiting satellites. But, you know, GPS satellites here on Earth orbit at low orbiting altitude, and they move very fast. Given that the moon is so much smaller and the gravity is less, they should be able to orbit closer to the moon, but they're going to be going even faster. So I don't know how that will skew their networking ability, but it'll be interesting to see what they do. I think they ought to put in a call to Elon and say, would you like to do Starlink a la moon? You know, because if they want to put 60 satellites in orbit around the moon to do this, that would be one launch for SpaceX.
Do you think those satellites will be visible to us through telescopes, maybe as little twinkles?
No,
Too small.
They're going to be way too small. But I'm sure that if you get the sun angle just right behind the moon as the satellite is orbiting over the limb of the moon, you might get a reflection. But you're going to have to try hard to see them because they're going to be very tiny, very far away. But don't let me stop you from trying. If there's a way, it would be an interesting photo. NASA Ames Research Center, in conjunction with SETI, they have a scientist working on meteorite contents, and they found water inside the Sutter's Mill carbonaceous chondrite meteorite. Now it's microscopic water, so it's not like, hey, we found a gallon of water. No, it's just it's like little pockets of water that the meteorite sealed inside of it, probably a billion plus years ago. The particular meteorite is called the Sutter's Mill meteorite. They're usually named from where they find the meteorite on the ground. So that'll be interesting because right now all they can say is the chemistry tells them the water is very CO2 rich. So it's CO2, it's CO2 tainted water, but they're going to do further studies on it. For example, examining the radioactive isotopic levels within the water, and that will tell them the age of the water versus the age of the meteorite, because the water might actually be older than the meteorite itself. So put a plug in that one and take a look at it, because I think there's probably going to be more things found out. NASA has said that they've tracked down at least one source for a fast radio burst. They can receive them via radio, and as soon as they receive one, they quickly tasked Hubble to point in that direction. And now they say they've found that the source is a star in a distant galaxy. Now, given the arc-minute or arc-second angular size of a galaxy, how they could narrow it down to a single star within that galaxy at that distance, it's like, I think, wishing doesn't make it so. The other thing they might not come to realize is that an FRB is an extremely powerful radio source. How do they know it's not coming from somewhere behind the galaxy, like someplace even farther away? So they're going to keep plugging at it. The ULA, the United Launch Alliance, has been trying to come up with a new higher capability performance launch vehicle called Vulcan. Catchy name, that. They're not quite there yet. Vulcan's not quite ready to launch anything. They're still doing test stand testing of the individual launch stages of Vulcan, but they have to launch something. So what they're going to do is they're going to continue to use the Atlas V, which has existed for a long time. Adam went away and he's coming back. Let me readmit him. Okay. So
excuse me, you said they have to launch something? Is there a reason they have to launch something?
Yeah, they get committed to launch things. The commitments from NASA are several years in advance to give them time to get their stuff together. Well, they didn't get their stuff together on the Vulcan launch system, but they do have the Atlas V launch system. And for the particular item, they're attempting to launch probably a military clandestine satellite because it needs a heavy launcher. They're going to use the existing Atlas V. They've been given approval to use Atlas V instead of waiting probably a few more years for Vulcan to be ready. But what they've done is they had created an upper stage, like a second and third stage for big launches. And the upper stage for Atlas has always been known as Centaur, Centaur. And they've modified it so that it can be launched by Vulcan. And now they're going to have to go back and remodify it to be able to be launched by an Atlas V. So I think they're really giving the United Launch Alliance, the ULA, a lot of latitude, and they would in no way give SpaceX the same latitude. So I would suspect that before Vulcan ever launches anything for NASA or for the military, you'll probably see that SpaceX is back to launching things because they've already got their proven heavy-duty launcher working. It's 3 Falcon 9 rockets strapped side by side. And that was the one where they launched it, and the 2 side boosters did a pinpoint landing back on the ground, and the center stage missed the barge because it ran out of fuel. Well, they didn't take into account that the third stage runs for a longer period of time than the 2 side boosters, but the next time they do it, it'll probably land on the barge, no problem. So
So
early,
they would have been, this way they don't lose any money, I gather, because they had a lot of time. Everybody was set up and paid to go at this time period, and
yes,
it would cause a lot of financial difficulties, and they would have probably got some kind of punishment for not sending something up.
yes, and there's actually evidence to that fact. Amazon's Blue Origin, they were going to have a different kind of rocket, because right now all they have is a suborbital, meaning it doesn't go around the Earth, it just goes up and comes back down. That's their new Shepherd rocket. They have a new Glenn rocket that they're working on that they have yet to actually launch. And NASA said, okay, you've got 2 years. And they said, it's going to take us longer than 2 years. Okay, we're pulling your contract. So NASA literally jerked around $200 million away from Amazon Blue Origin because they couldn't get their new Glenn rocket ready in time to launch what they'd already been contracted to launch. So ULA was in jeopardy for their Vulcan launch system because it's probably going to be out another year plus. So they were very concerned, and they went back and said, would it be okay if we built a few more of the Atlas V launch vehicles and launched using those? To which NASA and the military said, okay, for the heavy payloads that need to go into Earth orbit, the Atlas V is fine. But for the heavy payloads that need to go to the moon or to Mars, Atlas V won't be powerful enough. You're going to have to get Vulcan ready. And I guess they gave them another probably 2 years. And a year from now, if Vulcan's still not showing any progress, they could likely pull ULA's launch agreement. So
This
yeah.
is because there's so many people out there that want to utilize this equipment.
Oh yeah.
That they don't want to be tied up to people that aren't sending stuff up then.
Yes, it's not only the military and NASA launchers. They'd like to launch things. They've been given money to create spacecraft and probes and such, and they need launch vehicles. And if NASA's not building their own, Saturn V kind of launch vehicles anymore, then you've got to count on the commercial vendors. And if the commercial vendors, if you've got 3 different commercial vendors like they do, they have ULA, they have Amazon Blue Origin, and they have SpaceX. And if SpaceX is the only one successfully launching, you got to go with what works. So I can see SpaceX getting a lot more business from what Amazon couldn't do, and from what ULA might not be able to do. Now ULA is got a relationship with Boeing, and Boeing for years has always been kind of a backbone contractor for NASA launch capabilities. And if they lose out, it's a serious sign. So we shall see. Just another one of those, put a push pin in it, keep an eye on it. Let's see if Vulcan makes it to the next stage, or if they're flying Atlas V's until the contract runs out. So early on May 26th, we're going to have a lunar eclipse, and they're trying to line it up. It's going to be a blood red moon. It's going to be a wolf moon. It's going to be a super moon. It's like, okay, the moon will be new because that's when you have a lunar eclipse. The moon will be near perigee, which is its monthly closest approach to the Earth. That's if you mix a full moon with a perigee moon, that's a super moon. And because a lunar eclipse takes on a dark red color, it's the blood red moon. So don't let the media hype, overcome the fact that, these things happen from time to time. I was on with the Denver Astronomical Society's session yesterday evening, and they were all enthralled about being able to see the lunar eclipse. And then they did the calculations and found out it will be for 15 minutes just at sunset from where they are in Denver. So we're actually in a better position for it. We won't see it in full totality for a long period. We'll get a longer period, but it will be a not a totality for the duration. It'll be very quick. So try and see it if you want to. There's a new record resolution for microscopes now. It was something they started a couple of years ago, but they have final science on it. And they can now see individual atoms in an array of atoms. They post-process a lot of very fast images, kind of like we do with stacking astronomy images. And the end result is you can actually see a matrix of atoms, and you can see the separation of the atoms. So that if you're into looking at computer-generated images of atomic structures, that's interesting. And also in the nearly subatomic level, some of you might have heard of this stuff called graphene, which is a matrix of carbon atoms, usually 1 to 2 atoms thick, and it has very special electrical conductivity properties. But it's kind of challenging to make, and you make it and you don't get 100% production grade on everything that you make. So they're still trying to make new kinds of carbon atomic materials, and they found that, well, if you push them just right, you can make squares and hexagons. You don't have to make these very fancy chains, and they still come out with a lot of the same properties as graphene. So look for, these are called nanomaterials because they're pushing around atoms of carbon. So they're nearly subatomic. They're not subatomic because they're still using atoms, but they're very, very small scale. So they're to billionths of a meter. So they're nanometers. So take a look at that. And I had one more news item. Let me pull that up so I can get some detail on it. Earlier today, Virgin Galactic launched their first launch of their Spaceship 2. This is one of those commercial ventures where you pays your money, you get to fly suborbital, you get to feel weightlessness, you get to see the curvature of the Earth, and then you land back down in the aircraft as an airplane. So Virgin Galactic Spaceship 2.
Yeah, that's 55 miles up, I think.
Yes, they purposefully make it 57 miles up because that way you can get your astronaut wings according to NASA. The European Space Agency has a different belief that it should be 75 miles. But okay, we'll give them that. But for $250,000, once they go into commercial operation, you too can get your NASA astronaut wings.
They got about 600 people signed up.
Yeah. So I don't know how much you have to put down for your deposit. Is it the full 250K? But yeah, so commercial launched by very dedicated spacecraft for very wealthy people. Hopefully they won't lose too many of them on whoops. That would be a shame. I hope they have good insurance and good wills for their family that's left.
Travel insurance, like at the airport.
Oh, that would be nice. I'd spend $25 for $1 million travel insurance with them. I don't know if they just insure the rocket with Lloyd's of London, or do they insure the people flying on the rocket with Lloyd's of London too? I don't know.
When they have you check your baggage.
You don't get much baggage. You're only going to be up and back down for less than an hour. So, I don't think you need to carry even a toothbrush. So that's all I have, news that's fit to print, so to speak, for this week. Did anybody else find anything that I missed?
Well, there's a volcano that just erupted. Is that news?
I think that's news because that contributes to the CO2 pollution of the planet. And we've just let the biggest iceberg loose from Antarctica. I didn't want to get into that. There's too many global warming plus and minus folks. So where is this volcano located?
I used to know. I don't remember.
Is it in the Pacific Islands? Is
Is it the one in Iceland?
Iceland? Oh, okay. Don't get me started on how you pronounce them. They have Icelandic names for their volcanoes, and it's got 9 syllables with lots of consonants.
Never to be pronounced, ever.
Well, no. It's funny. You can actually go on websites where they have wave audio recordings of local Icelandic people pronouncing the volcano's name, and it's really funny to watch news media people trying to pronounce it, and the ones that are clever go, "Here's the name. I'm just not going to try." Or they'll actually play a video clip with a native pronouncing it.
A native, yeah.
And that's fine.
Only those can do it.
They have the same catalog.
Or you can just refer to it as the latest volcano on Iceland. Okay, and don't forget to talk about UFOs. Well, all I can say is you're really going to love next week's presentation from me. Can you see the Ingenuity Communication slide?
Yes.
Okay. So Ingenuity is the helicopter on Mars, and it's sort of been in the news a lot. And of course, I have to dig beneath the surface and find out everything that's going on, all the crooks and crannies and ins and outs of this stuff, because I'm a polymath and a techie kind of guy. So I did some research and actually looked at how Ingenuity communicates with NASA JPL back on Earth and followed the breadcrumbs all the way back. So that's what this is. Okay, so Ingenuity, that's the little helicopter on Mars. It was attached underneath the belly of Perseverance, and it dropped it down, and it's been doing a couple of little missions flying around. So it was a technology demonstrator designed to prove that, you know, aerodynamic things are possible even on a planet like Mars with an extremely thin atmosphere and where it gets really cold at night. Cold enough that you have to have a heater on to keep your electronics from freezing. So they had to modify the helicopter from what would fly on Earth, and they did that, and it successfully flew. But it needed to be extremely lightweight given the low atmospheric pressure, and they could only fly for 5 minutes or less at a time, and that's based upon how much weight the batteries are in the helicopter. So there's an algorithmic balance of, okay, we got to keep it warm at night. We got to make the counter rotating propellers, because it has no tail, counter rotating propellers go fast enough, and they have to be very long and very thin and at the right pitch so they can fly. And if you look in the center of the column, there's actually little adjusters for the tilt of the 2 different rotor pairs. And then on top of it, there's this little solar panel for charging it up so it has battery power for the next time. And it has carbon fiber, little springy legs, so it can even land not quite flat. It can land with a little bit of a bounce to it, and it'll survive. It won't flip over. So lots of algorithm going there to make the perfect helicopter for Mars, and they successfully did that. But our focus tonight is not on the helicopter itself. It's amazing. It's great. But if it didn't have a 2-way communication link all the way back to Earth, and what would it do? It wouldn't know where to go, what to do, or how to report it back. We wouldn't get any pictures from it. So here's the end-to-end path before we get into detail about it. So Ingenuity talks to Perseverance. Perseverance talks to multiple orbiters around Mars. The orbiters then talk to the NASA Deep Space Network, giant, Earth satellite dishes, and they've got several of those. But then it has to get the data between continents, because one of them is in Australia and NASA's in California. So you're not going to get a good linkage, fiber optic link under the Pacific Ocean for that. So there's this other satellite network called the NASA Space Network. And then that goes to the NASA JPL Deep Space Network Mission Control Center. But then the data actually has to get back to the Mars 2020 Mission Control Center, which is, they're both in NASA JPL's facility. They're just two different giant rooms. So that's how all the data goes end to end. That's like the quick picture of it. First thing you have to think about is communication with Mars is deferred. Mars is a fair distance from the Earth, and that distance varies based upon the fact that Earth goes around the sun almost twice as fast as Mars goes around the sun. So they'll be in different places at different times during the Earth year. So you have to point the antennas at different places. So there's no real live, real-time two-way communications with Mars because the distance is just too far. When we're really close, the light radio travel time could be 3 minutes. But as it is right now getting farther and farther away, it can take better than 20 minutes for one-way radio communication. So if you want to send a command that says, go do this, and then you want to get data back from it, it could take a couple of days. So you send the commands, you wait for their arrival, you wait for confirmation data to say it's happened, and then you wait for the bulk download of the big data afterwards. So, you know, Mars for a certain part of our year can be on the other side of the sun. There's a difference in rotational velocity. Mars is smaller than the Earth, but has a day that's about the same duration as the Earth. So it's got to rotate at a different speed than the Earth. And also, even though we're roughly 24 hours each other, you know, Mars and Earth, we're not in sync. You know, so our 0 degrees longitude doesn't port to their 0 degrees longitude. And by just being 37 minutes different, even if they were once pointing to one another, they're going to get out of sync. So Ingenuity is on a fixed location on Mars. Mars is rotating. Earth is rotating. They're both orbiting the sun. So the amount of time that there'll be line of sight radio communication is a tiny amount of time per day. And we're going to get into the detail of why that is. Let's see if this animation works in the shared zoom. So in the middle, you see the sun, and then you see the Earth, and then you see Mars. You see those little arrows? That's kind of like an Earth antenna and Perseverance on Mars. So I'm going to see if this animation works. And what you're going to see is Earth going around at about twice the speed of Mars. And Mars is also going to be going around the sun. And at the same time, both Earth and Mars are going to be rotating at roughly the same speed. And you'll see very quickly, if you watch the little pointers, they're very rarely pointing at each other. And so you don't have line of sight communication. So let's see if this works. There we go. Can you see the animation?
Yep.
Okay. So I have to explain the animation as this is PowerPoint. This is not like a video. So it's live animation. I did not draw them to scale because obviously Mars is much smaller than Earth. Because they're animations in PowerPoint, I loop them until I tell them to stop. So they actually start, speed up, go to an end, and then repeat. And when they do that, they kind of stop and start. Planets don't do that. They go continuously. But it does give you an idea that even if they were once pointing to one another, they aren't going to be pointing to one another after just one day of rotation. So that's the first complication you have is we're orbiting the sun differently, we're rotating differently, and things don't point to each other. Okay, the next thing is the communication data rate. As I stated, there's a large distance between Earth and Mars. There's all sorts of ways you can have junk noise in space. Think of those solar prominences. They produce a lot of static. There is Jupiter that has a radiation field. There is Saturn that has a radiation field. These produce static. There are pulsars. There are quasars. There's all sorts of stuff that produce random static radio bursts. If these bursts last, as they go past an area like Mars, they might last for a good portion of a second. So if the data transfer rate is very fast, like gigabit or megabit, then the amount of time each bit takes up in the communication is very short. But if the static radio burst is a good portion of a second, you can take out a lot of data with a single burst. And because there's no real-time data transfer, you can't say, oh, I didn't get that last packet. Can you send it again? That's, you either grab it and get it or you don't get it. So data rates have to be slower. This makes the bits wider. This makes it easier to detect the individual ones and zeros amongst the noise. Plus, there are what is known as Hamming codes. These are error correction codes. They will actually recover a few bad bits in each frame of the transmission. So if you're thinking megabit or gigabit internet is nice, deep space communication is more like not millions of bits per second, more like a few thousand bits per second. Now, obviously, the communication between Ingenuity and Perseverance can be a little higher speed, but higher speed data actually costs electrical power. So they had to drop its speed. So the communication path, which is line of sight, anytime you want to speak between Ingenuity and Perseverance, between the helicopter and the rover, is about 25,000 bytes, characters per second. Think of it this way. If you have an old style, low resolution camera that shoots, not megapixel, but 300K pixels in your image, and you're shooting in color, that's 3 bytes per pixel, or under 1 megabyte of data before you compress it. It takes about 37 seconds to send one of those images from Ingenuity to Perseverance, and even longer to get it back to Earth. So that's the data rate we live in. And here is a waveform. So we have a pictographic here. So up here on the left, we have the waveform. This is the digital waveform. It's ones and zeros. There is a radio frequency carrier onto which the ones and zeros are modulated, mostly in frequency modulation. And here's the signal that contains the data. And here's a noise burst. And the noise burst, I put at a certain width. And you can see that it literally takes out 1, 2, 3, a little more than 3 bits worth of data. Now, if I lower the speed and make the bits wider apart and fatter, and I put that same noise burst out there, I might take out 1 full bit of data, which with the Hamming code, I can correct in software. Now, this Hamming code is both directions. So when the Earth sends a command to Mars, to the rover, or to Ingenuity, it has to include the Hamming code so that when Ingenuity or the rover receives it, they can correct any lost data. And when it sends the data back to Earth, same thing. It has to send additional bits of Hamming code to correct any data when it gets back to Earth. So,
Can I interrupt you, Monroe?
Sure.
Okay. I'm trying to get this in my mind thought of now here on Earth, when we're doing data, we do it through like AT&T.
Yeah.
So NASA has developed their own communication program, and they have firewalls and all that kind of stuff because they don't want anybody to break into this, right?
The transmissions to the spacecraft have keys in them that originate from the NASA Deep Space Network, and it's pointing away from Earth. So if you wanted to say, I'm going to hack in and make the rover do wheelies for me, that would be impossible. But on the way back, if you wanted to receive a signal from the Mars Reconnaissance Orbiter, you can actually receive that signal. Now, if you have the software technology in your software-defined radio to decode the data, knock yourself out. But it's a very, very weak signal, and you have to do your own Hamming code correction. You have to know what the modulation is, and the modulation is not simply frequency modulation or amplitude. They're quadrature phase encoded modulation. So if you understand how to do all that radio digital stuff, you can probably come up with a decoder for it. I've decoded weather satellite data. It's not encrypted, and they actually want you to decode it. So it's kind of a fun thing to do. So if I really put the effort into it, and I did my research on the NASA websites to understand, and I built a radio receiver that could receive at that frequency and decode it, I could get the same stuff NASA does. But I'd have to have, a 20-foot dish in my backyard, and that's not going to happen. So if you want to listen in, you can do so. From Fox Observatory, we've actually picked up the signal, not decoded it, but seen the signal from the Mars Reconnaissance Orbiter. And the way we knew it was coming from Mars is, if you remember watching the movie Contact, if you think a signal is coming from there, you point the antennas away, and the signal goes away. You point the antennas back, and the signal comes back. That means that's the direction the signal is coming from. The next thing that you do is you say, okay, I know what the signal frequency is for the Mars Reconnaissance Orbiter. It's about 8 gigahertz. But I know there's a lower harmonic for that that's, a different signal strength, which is what I'm kind of seeing. And if I tune off of that, the signal goes away. And if I tune back onto that, the signal comes back. And the last thing that we did was knowing when the signal would be pointing back towards where you are on Earth. So when we get into discussing the NASA Deep Space Network, they have 3 receiving stations that are 100 degrees apart over the surface of the Earth. So as I was pointing out that, the Earth rotates and Mars rotates, and if they're both facing in the same direction, then that satellite receiver on Earth can pick up the Mars Reconnaissance Orbiter. But as soon as the Earth rotates, there's a gap where you can't talk to it, and then there's rotating for the next dish on Earth to pick it up. So you might start out as Canberra, Australia, and then go to Spain, and then go to California, and then it repeats itself. But at the same time, Mars is orbiting. So if you know when the Mars Reconnaissance Orbiter is being picked up in Spain, in Madrid, and you know about the time it takes to get it over to start receiving it from Goldstone in California, and you split that in half, that would be when the Mars Reconnaissance Orbiter is directly over South Florida. So if you point your radio antenna at Mars at that time, when you're watching it leave Madrid before it comes into Goldstone, and you pick up a signal in the direction of Mars on the right frequency, you're picking up MRO. It's not a good signal because you're not on the prime frequency, you're on some garbage harmonic, but you can do it. So, it takes techie stuff, but it's a fun thing if you're one of those polymath types that don't have any boundaries. If you stop me from learning it, I obviously can't learn it. But if you don't stop me and there's information available, I'm going to dig deep. Okay, so the next thing is the transmission distance. How far can things talk? Well, Perseverance on Mars can talk to the orbiters. There are several orbiters. These orbiters have different orbits, and we'll get to what their orbits are in the next slide. But there's the Mars Reconnaissance Orbiter, there's MAVEN, there's Mars Odyssey, there's the European Space Agency's Mars Express, and their ExoMars Trace Gas Orbiter. And depending upon the rotation and what you wanted to pick up, whether it's Curiosity versus Perseverance, because they're on different places on Mars, the NASA Deep Space Network may be relaying through different orbiters going around Mars. Now, the orbiters have a much bigger power budget than do the rovers on Mars. The rovers had to worry about, I only have so much weight I can actually land on Mars. If I make it too heavy, it may go crash instead of successfully land because the parachutes are only so big, and lots of power budget stuff there. But the orbiters, they can be bigger. They can have larger antennas. They can have bigger solar panels. They can have bigger batteries. They can amplify weaker signals with more power electronics. They can actually have critically cooled receivers and transmitters for very low noise. But if you're Ingenuity, the maximum distance between you and the rover is about 1 kilometer. So they're only going to fly Ingenuity out ahead of Perseverance by about maybe 1/4 to 1/2 kilometer, because they always want to have a good signal. They don't want to take it out to the edge.
Yeah.
So that's about as far ahead as it can get. It's about 1/4 to 1/2 kilometer, which is not much, but they're going to try it. And if they extend that out to 3/4 of a kilometer and they can still get a good signal, that will give Perseverance a 3/4 of a kilometer head start. So it's viable. It's useful to do that. So Ingenuity talks with Perseverance, which talks with the orbiters. Now, there are 2 transmitters on Perseverance. There is a very, very low speed, low power transmitter that can actually get all the way back to Earth, but it's only for basic, are you still alive kind of data. The scientific data actually goes through an orbiter. The orbiter sends it back to the NASA Deep Space Network.
That makes sense.
So let's talk about orbits for a moment. We've got a planet, in this case Mars, and it's got these multiple satellites that are orbiting it that we use as communication relays to get back to Earth. The eccentricity, or the egg-shapedness or ellipticalness, or how elongated an ellipse is, different definition. These are all parameters in the ephemeris of the orbit. So if I'm orbiting a satellite, let's say around Earth, and I want it to be a geosynchronous satellite, I'm going to put that in equatorial orbit. So it's always going to point at the same spot on the Earth at the same time, because it's going at a speed, an orbital velocity, that will keep it over the same spot at all times. But if the place I want coverage on is not quite, within a certain latitude of the equator, now I've got to tilt my orbit. I'm still in a circular orbit. I still may be geosynchronous, but it's tilted so I can get to a different spot. That's called a circular inclined orbit. If what I want to do is to create a stripe pattern of gathering data, I can actually put it into a polar orbit. And if I make that polar orbit at just the right distance and just the right speed, so that every time I go back to the North Pole, there's been one full rotation of the planet beneath me, then every day I can get a complete sweep of the planet. That's called a circular, polar, sun-synchronous orbit. There's another kind of orbit that's also equatorial. That's an elliptical equatorial. That's where I need to get my orbiting spacecraft close to something that's on the surface, but I need it to be far away from the planet for communicating back with Earth. So I have this very long elliptical orbit, and I can tilt that ellipse. And when the ellipse is inclined and rotated, that's actually a Molniya orbit. That's named after a Russian who came up with this particular kind of orbit. It's very useful. That's actually the kind of orbit that the China Mars orbiter is in right now, is a Molniya orbit. You can take this and combine that with the sun synchronous, and you can actually come up with an elliptical polar orbit. And a number of spacecraft that are orbiting the moon have elliptical polar orbits because we want them to get really close to the planet at certain times, and they need to get far enough away on the other time. So if we want to go really close, and we have to go really fast. And if we go really fast, we have to make it elliptical. Otherwise, it will be in a degrading orbit and fall back down. So it goes into this high energy elliptical orbit. And every so often, it'll go whizzing past a particular spot on the planet or moon. So that's the different kinds of orbits that are out there. Now we're going to go into, well, you got a variety of these orbiters going around Mars. What kind of orbits are they in? Because these orbiters are relays for the various things that are on Mars, like Perseverance, Curiosity, Insight, Beagle 2. All these things need orbiters to get back to Earth. So Mars Reconnaissance Orbiter is in not quite circular orbit. It's inclined 90 degrees, so it's kind of polar, but it has a period of 112 minutes. So it's a very fast polar orbit. The Mars Odyssey Orbiter is in a circular orbit, and it's 93 plus degrees inclined, so it doesn't interfere with MRO. But because its orbit is a little different, it's 120 minutes. So it's also going around very fast. So you can tell from these two orbits, when they fly over Perseverance or Curiosity, and Perseverance with Ingenuity, then if the entire orbit around Mars only takes 120 minutes, they're not going to be overhead of the lander for very long at any particular time. They're certainly not asynchronous like a geosynchronous. Then there's Maven and Mars Express, which have very elliptical orbits. So Maven has a 270-minute orbit, which is longer, but because it's elliptical, that means that it's not going to spend very much time above the surface of Mars at its closest approach. So it's going to be a slow whip kind of orbit. And Express does the same thing, but it's a little farther out. So 450 minutes instead of 270 minutes. So again, it's, it's going to be out here a much longer period of time before it whips by. The ESA's TGO, it's in a circular orbit. It's inclined by 74 degrees. And the reason for that is the thing they want to get data from is not polar. It's down at a tilt. So it's 74 degrees and it goes around 12 times a day on Mars. So it's a lot like low Earth orbiting satellites that go, every 90 minutes they go around the planet Earth. Well, the TGO orbiter is the same kind of thing. It's going around Mars 12 times a day. But it's in a 250-mile orbit, so you have to compromise how far away the orbiter is from the surface as to how much radio power it's going to take to pick it up. Now, in order to get to Perseverance and Ingenuity, which are in Jezero Crater, for more than a few minutes at a time, you're going to need not just one orbiter, it's going to need to switch between orbiters. And since they're on different orbits, every time an orbiter goes by, you're going to have to move Perseverance's antenna to point to where that satellite's going by, and the antenna's got to move to track the satellite. And that way they can have the longest possible period of time in contact with the orbiter. What all this amounts to is, non-trivial calculations as to, okay, I'm Perseverance sitting on Mars. I need to communicate with one of 6 different orbiters. Which one's coming overhead right now? Where do I point my antenna? How fast do I move the antenna? And that way I can talk to the orbiter. That's just to talk to the orbiter. Now the orbiters are talking to the Deep Space Network, and they have the same sort of dance to get back to Earth. So the Deep Space Network We have 3 sites: Goldstone in California, Madrid, outside of Madrid in Spain, and outside of Canberra in Australia on the east coast of Australia. They're separated by 120 degrees. If you're in low Earth orbit, you're too close and they cannot give you 24-hour coverage. If you're much farther from the Earth, you're deep space, and therefore they can give you 24-hour coverage. So NASA has to operate the deep space network 24/7, and they operate it out of a control center at NASA JPL in California. The Mars 2020 Mission Control Center is in a different large room at NASA JPL in California. So each one of these DSN sites, they have several size dish antennas, and use different antennas based upon what they're trying to connect to. If they're trying to connect to, Voyager 1 and 2 at the outskirts of our solar system, they're obviously going to use the 70 meter, 230 foot largest antennas. They found out recently they can actually gang up the antennas because they expect Voyager to get so far away that even the one 230 foot antenna each site will not be good enough. And they'll have to gang up multiple antennas to get a signal. These are actually critically cooled receivers. So they actually have, liquid helium and liquid nitrogen cooling the receivers to get rid of noise. So when Perseverance communicates with the orbiters, it actually talks at 2 megabits because it's short distance and it's got a little protection with Mars's atmosphere. So it can talk at a higher rate. But once it starts talking to Earth, that's different. If Perseverance on the UHF low band wants to talk directly to Earth, it can talk to Earth at 160 bits per second, up to a maximum of 3K bits per second. So it's literally, the only thing we're going to use that for is, are you still alive? It's a back channel. Mars talks to the satellites orbiting, the Earth DSN talks to the satellites orbiting Mars. Depending upon the distance, if it's close, it can be as high as 2 megabits. As it stretches out further, it can get down as low as 128 kilobits. So theoretically, this allows for the deep space network to talk to at least one orbiter almost, but not fully, 24 hours a day, because the orbits don't give them full coverage. If all the orbiters are on the other side of Mars at any particular time, away from Earth, as Mars rotates and Earth rotates, you can't talk. So there'll be a window of silence. And this is when they let the Mars 2020 science team sleep on Earth, the humans. So they operate on a rotating 23.5-hour day. So when the satellites are on the far side of Mars, can't talk. Also, Earth is tilted on its axis. Mars is differently tilted on its axis. So you have different satellites at different orbital speeds. So, plus the NASA Deep Space Network has other missions not pointing at Mars at all that they also have to support, like the Juno mission, which is at Jupiter. So at least one of the antennas has to be pointing towards Jupiter, which is farther away than Mars. But luckily, Juno has a lot of electrical budget, so it has stronger transmitters, and they can use smaller antennas. Then there's the Stereo and Parker probes, which are going around the sun. So
Monroe,
yes,
I'm trying to relate things to what I know.
okay,
And one thing is that the telephone company came out, FPL, and did some training for courtesy on the phone. But during their courtesy training, they also taught us about how phones relay and their delays because of the curvature of the Earth and because of distance and things like your. So it is, and you're talking about that there's a time period that they can't talk because they're behind the planet.
yes.
And so And they're not making noise when they're talking. It's a data type thing, right?
Yes, it is data, but there are other things in this universe that make staticky noise that can disrupt the communication.
Okay, but they're not making the staticky noise.
No.
It would be something else that would be interrupting it.
Yes.
Okay.
It is not ground-based radio frequency interference. The particular radio bands that NASA uses, it is verboten for amateurs to use those for radio frequencies, and it is also verboten for misbehaving electronics to be putting out interference in those frequency bands. They're up in the multiple gigahertz level, so the dominant deep space network downlink is at 8 gigahertz. So you have to have special kinds of transmitters, special types of antennas, and average stuff doesn't transmit in those frequencies. So there's not a lot of RF interference from things on the Earth interfering with the NASA Deep Space Network. It's more like the broadband natural noise bursts of the universe that cause problems.
Oh, we have natural bursts in the universe?
Oh, absolutely. What's a pulsar? A pulsar, it's a rotating neutron star that beams out wideband noise.
Oh.
It's static. So we have to deal with those. And if for example, if we're pointing towards Mars in its orbit around the sun, and there happens to be a Earth-aligned pulsar directly in the line of sight to Mars, if that pulsar were putting out noise at 8 gigahertz, the signal would be completely obscured. Couldn't receive it. Luckily, pulsars don't put out signal at 8 gigahertz. They put out signal at a much lower frequency than that. One example of something that we it's a natural noise source and there's no way around it because it's very broadband, is the solar orbiting probes like Stereo, Parker Solar Probe, those things that are going around the sun, when they are close to being behind the sun, we can't get a signal because we're literally pointing the antenna towards the sun. And when you do that, just as your telescope would be blinded by the light, your radio receiver would be blinded by the broad spectrum natural noise coming from the sun. So, radio can be interfered with.
So how much of a delay is there? Is it 15 minutes of a delay between
right now,
the time they speak it?
Right now, the one-way delay between Earth and Mars is around 20 minutes.
20 minutes.
So if I go, hey, Ingenuity, do this. Me saying that will take 20 minutes to get to Mars Reconnaissance rover, which will take a fraction of a second to get it down to Perseverance, which will take another fraction of a second to get it to Ingenuity. Ingenuity will do it and then report back, I've done it. And then it goes from Ingenuity, Perseverance to an orbiter, 20 some odd minutes back to Earth. So the round trip time is about 42 minutes. It's like saying hello, and then waiting 40 minutes to get back. Hi.
Yeah. That would be quite a delay there. But I gather it's quite amazing in another way.
Well, it is amazing that we can communicate at all.
Yes.
And it is very amazing that all of this technological magic is just matter of fact done, because if it's not done perfectly, you lose communication with your multi-billion-dollar space probes, and that's not good. So you don't mind spending $500 million a year to make sure you can do this with high quality.
Yeah. Now, what does the JPL stand for?
Jet Propulsion Laboratory.
Okay.
That's kind
so
of.
They're the ones that do the communication for us.
Yes, they have an affiliation with the University of California, Caltech. So JPL is literally adjacent to Caltech property. So they have affiliation with the university. So they will actually extend out some of their science programs to Caltech graduate students. Kind of saves by not having to pay them. But the operations center for NASA JPL, there's a number of them, and they're in California.
What is it again? It's JPL is the, what is the abbreviation again?
Jet Propulsion Laboratory.
I've heard of it. Jet Propulsion. It's a very popular name.
Yes, it started out as the aerodynamic laboratory for the precursor to NASA. So when we wanted to fly things faster than sound in the Earth's atmosphere, we looked at JPL at kind of being the jet engine aircraft designer folks. You know, prove this out before commercial vendors spend money on making things that don't work right. So they proved it out. And then when we needed spacecraft, not the launch vehicles, because those were out of Goddard Space Flight Center in Alabama. But when we needed the spacecraft themselves, we looked at NASA JPL for the rocket propulsion technology from a design level, you know, what's feasible, how to high-speed pumps work and such. But the people that actually built them were in Huntsville, Alabama. So NASA is a very large organization. It has many branches. It is actually a unit of the U.S. military, for the people that didn't know. That's why sometimes NASA flies things that are clandestine for, I don't know, the NSA, the CIA, the military, because they are an arm of the U.S. military. But JPL is the operations folks. There is kind of a NASA JPL branch in Texas, in Houston, Texas. If you remember the moon landing center, that was in Houston, Texas, because we had a vice president who became president who said, let's spend some money in my state. Okay, stop spending money in Florida. The tricky thing was that the launch of Saturn to the moon actually took place through a command center in Florida. And the moment it left the launch pad, all of the communications were flipped over to Houston.
Houston, we have a problem.
Yes. Houston,
Now,
we had a problem. Somebody forgot to flip the switch.
Yeah, it's not launch control anymore.
Yes.
now it's not, it's going to be all under the Space Force. I gather I haven't heard anything about disassembling Space Force.
Well, there is a branch of the U.S. Air Force called Space Force, and Space Force is the space operations arm of the U.S. Air Force. So when the U.S. Air Force wants to launch something, be it a spacecraft, probe, people, whatever, that launch is under the jurisdiction of the U.S. Space Force, which is part of the Air Force. So
I thought there was a separate branch.
Well, you could say things like, what is the Coast Guard? Well, that's a branch of the Navy.
Okay.
What are the Marines? The Marines.
You're right.
The Marines are a branch of the Navy.
The Navy.
What is
right.
the Navy? That's a branch of the U.S. military. So there's all sorts of jurisdictional governance. So there is the Kennedy Space Center in Florida. There is also the Canaveral Launch Station that's in Florida. Canaveral was military, and Kennedy was NASA. So
they're in the same area?
Oh, they're all in Titusville, Florida, yeah. But when they came up with the Space Force, they rebadged the Canaveral Air Force Station to the Canaveral Space Force Station. I liken it to, well, it's the same people doing the same job. They just have different emblems on their uniform and different signs on the buildings and different logos on the paperwork. One of the things I always used to kind of joke at is If you go to a gas station and you look at the gas station pump, there's a little decal on the pump that says, you know, it's been certified and calibrated by that particular state's, usually agricultural division of that state. And every time there's a new person elected to the head of agriculture, all new stamps have to go out because that person's name is on the sticker. That's a huge waste of money. So every time they shuffle around department names and change logos, all the insignias on all the uniforms change, all the logos on the outsides of the building change, all of the logos on all the paperwork change, all the signatures of all the emails change. It's many, many, many millions of dollars, your taxpayer dollars at work, just to change the name. But it's the same people doing the same thing. They just have a different division they report into. So the Deep Space Network has these 3 places on Earth with different size antennas, and they can kind of talk almost 24/7, but you can't relay through orbiters that are on the far side of the planet, and everything's tilted in. The Deep Space Network has other missions they also have to support, so can't devote everything to Mars. And for those of you that might want to see the Deep Space Network in action, NASA actually has a website called Deep Space Network Now. It will actually tell you what each of the 3 sites are communicating with. And if you look at, for example, in this case, Madrid has just got a test signal going. It doesn't say what it's talking to. When it's talking to something, you'll actually see a name below the antenna, and you'll see what looks like 2 sets of lightning bolts. So it's not only sending out, it's getting it back. So this is the SOHO. This is a sun orbiting spacecraft called SOHO. They all have little acronyms. The next up satellite that antenna number 55 is trying to listen to is Juno around Jupiter. Now, since SOHO is the sun and Jupiter is Jupiter, obviously the antennas aren't both pointing in the same direction. They're pointing in different directions. The big antenna is trying to listen to something farther away. This is called Grail, GTL, and it's right now waiting to receive a signal. It's not yet getting it back. Sometimes they'll just put a test signal out just to make sure the transmitters are working, and you'll actually see it say DSN. This is a antenna in wait. They're waiting for the, I forget the name, but GSSR, Global Surveyor, I think it is.
I'm going to pick you up, okay? I'm going to pick you up. Ready? Here we go.
Okay, and Canberra in Australia, antenna number 43, is about to listen to the Mars Express and the Mars Odyssey, M01MO. That's Mars Odyssey. And this antenna is about to listen to MAVEN. And this antenna is about to listen to the Mars Science Laboratory. That's Curiosity. So you can see, hey, when Earth is lined up, line of sight with Mars for a particular antenna complex like Canberra, they're going to have all the antennas pointing in the direction of Mars for all the probes they can communicate with at the same time. So that's the actual link, is eyes.nasa.gov, DSN, HTML. But you can actually just shorten that up and drop off the DSN HTML and take you to the home page. And then you can play around. You can say, hey, what's this satellite looking at? And then it'll show you pictures of the satellites, and it'll tell you how far away they are. It'll tell you what the light travel time is. It'll tell you what the wind speed of the antenna is. In case the wind's going too fast, they can't tilt the antenna. So there's lots of little juicy tidbits, but that's the Deep Space Network Now page. Okay, the NASA JPL site. So the Deep Space Network talks to the NASA JPL sites. Now, in the case of Goldstone, which is in California, and NASA JPL, which is also in California, they can talk very high speed over a fiber optic link that runs up, the California coastline. So that's really great. However, when the DSN site that you're trying to get to is Madrid, Spain, there is a fiber optic link that goes, from the United States to Europe, but it hops through a number of countries, which increases the travel time. So rather than making the data transfer time longer by hopping through all these things, or going trans-Pacific, which is even longer, what they'll do is they'll lower the data rate from gigabit to, a couple of hundred megabit, and to keep the transfer rate low, they'll actually go through satellites. So NASA has the Deep Space Network, DSN. They also have the non-deep space satellite network, the SN. So they'll use the SN to communicate between continents on the Earth. And if you really polymath into it, there is actually a NASA handbook on communication using the Deep Space Network. And it tells you the ins and outs. So if you're somebody at NASA and you're planning out, let's say, a next generation probe for Saturn, it'll actually tell you what slots are available and when you can communicate at what power levels. So there's a design handbook. So this is the NASA Space Network. And there's lots of satellites orbiting the Earth. These are geosynchronous satellites. So depending upon where you are on the Earth, there'll be a different satellite you'll want to talk through. And you'll point your ground antenna to a different location. So there's a number of major satellite tracking systems, and they want really good signals that they can talk at really high speeds. So they have very large dish antennas. And some of them are in places where the weather is not always that great, and they don't want it to be damaging the antennas. So they put them inside of these giant fiberglass radomes. And they even have for specialty communication purposes, like McMurdo Station in the Antarctic. Well, we'd like a faster communications link. So how do we get that? Well, you build the McMurdo Station on the NASA Space Network. So this has actually been built in the last few years. This is the McMurdo NASA Space Network Station. Now, people talk about, these Starlink satellites and how big they are and how much radio interference they produce and how their solar panels produce a lot of reflection, and you can see that from Earth. And, okay, take a look at these satellites. These are called the TDRS, the Tracking and Data Relay Satellites. These are satellites that NASA puts up into orbit, and they actually put out newer, bigger, faster satellites. Each of these satellites is the size of a Greyhound or Trailways bus. They're very large. They have to be launched into orbit with very big launch vehicles, the biggest that we have. They put them up there. They have multiple antennas that are 15 feet in diameter. They have solar panels, dual solar panels that are hundreds of square feet in real estate. And they point down, the backside of them point downward to get a good, strong power connection with the sun, because they're always pointing away. They also have multiple smaller antennas. So you can actually see these satellites if you go to like Heavens Above and look for the TDRS satellites. You can actually see these things, and they just sit there all the time at an angle overhead. And when the sun is just at the right angle, they're essentially a glare bomb. So you talk about the Starlink satellites obscuring optical astronomy. These things are up there. They're put up there by the US military for purposes like military and NASA. They don't care how big they are. They don't care how reflective they are. They are there. You deal with it. And they're putting up bigger and bigger ones every few years. And these two that are offline, the ones that are gray over here, and they just leave them up there. They deactivate them, they put them into a parking orbit, and they're geosynchronous, so they're not coming down for hundreds of years. But that's the NASA Space Network. These are orbiting satellites around the Earth, and they relay between each other. So if I am in California and I've got a satellite directly overhead, and I want to talk to somebody over in Europe, I can actually communicate with the TDRS satellite directly above Goldstone, California. It will relay satellite to satellite to satellite to satellite, and then send down to someplace over in Europe. So that's the TDRS satellite network, and data coming from Mars actually goes through the Deep Space Network, and depending upon where Mars is in its positioning relative to the Earth's rotation, it may take it through the NASA Space Network to get to NASA JPL in California. So this is just another part of the stuff that's got to work 100% or no Ingenuity for you. And it's just, stuff that works in the background. People aren't even aware of it. So this is not secret. This is all public information. You just have to go scratching for it to find it and go, oh, that's cool. How does that actually work? And there's, I grab these images from NASA sites and from military public sites to just go, here's stuff you didn't know about. So when you're driving through a particular part of the US and you see this giant antenna farm off in the distance, that's what they're doing. They're talking to these satellites that are in orbit, and they have giant antennas, and there could be dozens of these antennas. That's what they're doing. They're talking to stuff, and they do it all the time. And nobody ever asks for your permission before they do it. They just do it with impunity, just like UFOs.
Yeah.
Okay, then the communication window. How often can you talk to something? Well, let's see. Everything's rotating and orbiting. The orbiters are available only certain times. So you've got these slots, and you know when the slots are going to occur because you can do the math. So you pick when you want to do something. And you may find that, oh, I want Ingenuity to fly. Well, what's a good daytime period of time for it to fly? Because that way there's lots of sun to recharge the batteries, so that evening when Mars is in darkness, the electronics don't freeze on Ingenuity. So think about that. Then you switch that in and you go, okay, when do I send the command to be relayed to Ingenuity? I have to send that maybe a day in advance because it's got to go through all this stuff to get there. And it gets there, and it does its thing. Now, when am I going to get the data back? Well, the first slot of opportunity to send the data back may be a short window. Well, during a short window, you might get one of those black and white pictures from a camera that's color. Well, the camera is actually red, green, blue. It's actually 3 monochrome cameras with filters on them. And what they'll do is they'll pick one of them, like red, and they'll send you a black and white image back. Because the black and white image is a lot less data, and you can probably sneak that in through one of these small slots before waiting for it all to come back when you have a really good window of, maybe an hour to send stuff. So that's why you get signals first, then you might get a black and white photo or two, and then you get the color, higher resolution stuff a few days later. Things take time. And then there's sharing. Just because Ingenuity is like, the latest piece of shiny metal, doesn't mean it gets all the resources. When Ingenuity wants to do communication, it has to talk through Perseverance. When Ingenuity wants to fly around, they want to have the cameras on the mast of Perseverance pointed towards where Ingenuity is going to fly. So if something goes wrong, they have video of it, a picture of it. When you want to relay the data to Ingenuity or back from Ingenuity, Perseverance is occupied because it has to talk to the orbiters for, doing something on behalf of Ingenuity. Fine. That occupies things on Perseverance. So you might find that the sensor that does, let's say, radar on Perseverance can't be operating at the same time that they're doing radio communications with Ingenuity, because we have a conflict in use of transmitter bandwidth. So, you know, when Ingenuity is doing something, Perseverance has to take a back seat on the science that it wants to do. And you only get so much Ingenuity time before Perseverance goes, hey, my turn. And you do a little Perseverance science in which Ingenuity has to sit over there and be quiet. So that's why you see these flying opportunities. It gets to fly sometimes, but not all the time. So once Perseverance gets a lot of its science sessions done, we may see Ingenuity doing a lot more free flying as a look-ahead scout for Perseverance. So that's sharing. You got to share. And all these orbiters that you're using time with, you have to share their bandwidth as well, because they've got their own missions. And so you send back all these images, you send back all this radio data. How does all that get processed? Well, NASA used to have supercomputers that would do this. And there's a great place in San Diego, California called the San Diego Supercomputing Center, which your tax dollars built and keep going. But now they, you know, under commercial contract, they make money selling services. Okay, David went out and came back again, so we'll read it with him. So rather than NASA trying to always keep the fastest, most capable computers, they've started to commercially outsource that. And as more and more NASA missions come into existence that are running simultaneously, that's more and more data that has to be stored. And these radio things that they're doing, the radio antennas, the radio astronomy, those aren't just megabytes or gigabytes or terabytes. Those are petabytes. So thousands of megabytes of data per day. And NASA's not going to build the storage to hold all of that. So they outsource that to commercial cloud storage farms. So the computational processing is bursty. It's variable. So at the time of launch, there's no signal coming back from the probe because it's sitting silently inside the launch vehicle. So not a lot of computation needed. As the probe is going to, let's say, Mars, periodically there's some data that has to be analyzed. You know, when it flips around and takes a picture back, there's some data, but it's idle most of the time. Not a lot of computational. Now, once it arrives on Mars and they want to do science and get data back and do analysis, it takes a lot more computational processing. So it's bursty, and it's not good to spend taxpayer dollars building these massive supercomputing centers dedicated for a specific mission like Perseverance. Much better to pay money to the likes of Amazon, Microsoft, and Google to do all that, create fast computers for you, and we share time with them. NASA first started doing this commercial outsourcing back when Spirit and Opportunity were on Mars, primarily for the back-end data storage. They didn't want to grow out these server farms. There was not a lot of data processing going on, but storage. So that, you know, Spirit and Opportunity data is stored on the likes of probably Amazon, which is where they started. Then they went out to Microsoft for a lot of the server processing, and then for the bandwidth, Google. So it's a mix of Amazon, Microsoft, and Google that are commercial contractors for NASA JPL cloud computing for both processing of data and for storage of data long term. So cloud computing becomes a part of this whole deep space data processing. So now that, if you remember from the beginning of the presentation, there was that little straight line: Ingenuity, Perseverance, Orbiters, DSN, Mission Control. Here is more detail. So Ingenuity talks to Perseverance. Perseverance talks to one of multiple orbiters, depending upon where things are overhead. which talks to one or more NASA Deep Space Network antenna sites, depending upon, where Earth is pointing and where Mars is pointing. And if it's across continents like Australia back to California, it may go up to Earth orbiting satellites and then back down again using the TDRS network. But that just gets you to the Deep Space Network Mission Control Center, and then it has to get piped to the Mars 2020 Mission Control Center, which they don't handle it directly. It goes to cloud computing and cloud storage, and then what the public sees comes as a result of that. And to give you an idea of the processing capability, Perseverance can actually do its own selfies now. If you remember Curiosity taking selfies, that's where it will take snapshots with the mass camera all around. And when it's over here, the arm is in the way, so you can see the arm in the picture. But when it's over here, the arm is not in the way. You're looking at sort of the open gap beneath the arm to get down to the top of the rover. And there's software that can actually patch all that together. And all of a sudden the arm disappears and all you see is a overlooking shot of the rover. Well, what took the picture? Well, the rover took a picture of itself, but it's not a one shot. It's you shoot all the way around, and then you have the software glue it all together and remove the arm. And that's how you get these selfies of Perseverance and Curiosity. Curiosity was the first rover to do that, but it did it using data processing back here on Earth, or the cloud computing. But Perseverance actually has enough onboard computing capability. The computer on Perseverance actually runs Linux, a variant of Unix. So it has enough horsepower to do that on board and just send the stills and the resultant selfie back to NASA. So as we get smarter, faster processing on the rovers, they get to do more of their own work for themselves rather than sending it back to Earth and us doing it on cloud computing. So all of this has to work soup to nuts every time, 100%, or you don't get the data back. You can't command the probe on another planet. And most people just kind of don't know about this. And I won't say take it for granted. If you knew about it and you just assumed it all worked, that would be taking it for granted. But if you don't even know it exists, that's just, it's magic and it happens and I don't need to know. Well, sorry, you're watching one of my presentations, so you may not need to know, but there's information.
Yes, it is.
I wonder how China is doing it.
Thank you for that precursor, because if I click right here, look, here's a slide specifically regarding the latest China orbiter, lander, and rover and how they're doing it. Now, obviously, China's not using NASA's Deep Space Network or NASA's or the European Space Agency's orbiters around Mars. They have to do their own thing. So people may have taken kind of a slighted eye at the rover that China put on Mars because it's not quite so rapid and abundant with pictures. That's because the orbiter, and we only have one of them, is in a highly elliptical orbit, so that when the orbiter is overhead over the rover, it can use a higher speed signal. Because it's closer, the delay time is less, and the ability to get a megabit signal down to the rover from the orbiter is better because the distance is closer. But it's also going to be zooming at that low altitude much faster, so it has a much smaller window to contact between the orbiter and the rover. And when the orbiter wants to communicate back with Earth, it has to be on the elliptical elongated side, because that's the only time at which it can point back to Earth with its antenna. So it has even slightly more complicated means of communication. Now, China does not have a fully covering 120-degree network on Earth. So what they actually rely upon is a few satellite stations on Earth majority of them is in China, but China is a very wide nation. So they can have, 120 degrees twice in just China. They can do almost 240 degrees. So they cover a good portion. But there's another gap they're missing, which is North America. Well, obviously, we're not going to stand up a China receiving station inside the United States. That, I think, it would be a great idea. I mean, we have car manufacturing plants from Europe and Japan. Why not have a China Space Network antenna farm somewhere on Earth? Because people would be afraid of it. I understand. So what they did was they went into an agreement with Argentina, and in Patagonia, which is down towards the bottom of Argentina, China has an Earth satellite station. And they can use the stations they have in China, plus the one they have in Patagonia, plus 2 orbiting satellites to create their effectively 24/7 network. But because the orbiting satellites are only facing in a particular direction based upon their orbit, when they want to switch from, let's say, the China probe on the moon versus the China probe on Mars, they have to retarget the 2 satellites, because it's one thing to point to Mars, moon's over there, gotta point the ground stations to the moon, but you have to point the satellites to the moon as well. So much more complicated. And somewhere along the line, they decided, and we're going to change the name of our flight control center. They don't have like a deep space network control center and then a particular probe control center. Everything is all in one. It's a very busy command center. It's called the Beijing Aerospace Flight Control Center, obviously in Beijing. They do have a supercomputer, though. It's not a commercial supercomputer. It's Chinese government-owned supercomputer, and it's actually called Divine Might. Don't take it as a military gesture, like they're showing how mighty they are. The Forbidden City in Beijing, which I've actually been to, it's a large part of the very old part of Beijing, and it has gates, north, south, east, west. And the gates all have different divine names, like divine power, divine light, divine might. So the Divine Might supercomputer is named after the northern city gate to the Forbidden City in Beijing, and that gate is called Divine Might. Cool. I find this stuff just, very interesting. All the little connections back to, and why did they call it Divine Might? Is that like, a superpower play? Nope, just happens to be the name of one of the gates in the Forbidden City. So now you know how even China does it. Here's the funny tidbit. The Mars lander and rover by China landed in Utopia Planitia. And if you're a fan of Star Trek and you get into the details, the Enterprise Galaxy class vessel was built on Mars at Utopia Planitia. And NASA, when they landed their Viking 2 lander in 1976, the Viking 2 lander, it's not a rover, it doesn't move around, it just plopped down in one spot and did all its science from there. It landed in Utopia Planitia, because back in 1976, we were afraid of landing on bumpy ground. Utopia Planitia is a lava plain that is very smooth and flat, so it was an easy target. If we were off by 100 miles, we would still be landing on nice flat ground with no mountain ranges or big rocks, which is exactly where China decided to land their first rover, was in a place without a lot of unexpected rocks that could damage the lander or the rover. Great minds think alike. But the neat thing is, China's rover, Zhurong, can actually drive over to where the Viking lander is and say hi. So we may eventually see pictures from China of what the Viking 2 lander looks like these days. The Viking landers were not powered by solar cells because NASA was aware that, NASA was aware that Mars has dust storms which could cover solar cells and cause the lander to be unusable, which has happened. Spirit and Opportunity, which were powered by solar cells, got their solar cells covered in dust, and nobody's going to go up there with a brush and blow it off. So they were declared dead when they could no longer charge their batteries and their electronics became frozen. The Viking lander was powered by a plutonium radioisotope thermoelectric generator, kind of like our deep space probes, kind of like Perseverance and Curiosity. Now, even though these landers are supposed to last for a couple of years, their power generation capability lasts for decades, easily. The Voyager 1 and Voyager 2 space probes, their power is also RTG based, and they've been going strong for lots of decades, and they can still generate enough electricity to send back to Earth. So if Viking 2 was shut down due to a lack of ho-hum, we're just bored with it, turn it off, and they can still turn it back on. I was actually in a NASA JPL online conference a couple of days ago, and I actually put in the chat window. So if you guys are really aware of the Chinese lander and rover and such, and you know it landed in Utopia Planitia, and I know that Viking 2 is sitting there, is there a possibility for you to turn Viking 2 back on so you can take buddy pictures of each other? And the only thing I got back was a little blurb that said, interesting. They didn't say anything. So maybe they'll think about it. But if they've had it turned off this long, all the electronics probably froze, and any moisture that was inside the electronics crystallized, and ice crystals speared all the electronics and destroyed it. But it would be interesting to have the rover from China drive over the Viking 2 lander and have them take pictures of each other. That would be, I think, really cool.
Silly. But funny.
So it's after 11, so let's get to some conclusions here. So what have we learned from this? Everything in space is moving. Radio communications requires line of sight, so things have to be pointing at each other for you to talk. Things in space can be far apart, and light only goes so fast. So as you go farther apart, it's going to take more time. Earth to Mars right now, 20 plus minutes one way, 20 plus minutes the other way. The other thing is transferring data over deep space distances due to all of the naturally occurring staticky noise bursts has to be done at a low data rate for reliability. You want to get a quality signal? Make those bits fatter, so if static goes in and smacks a half a bit, you still got enough to detect the rest of the bit. Mission craft have a size, weight, and power budget that limits what it can do, how fast it can transmit, and whether it has to transmit locally and then relay up and then relay back to Earth and then relay to California. So that's a budget. It's a formula. How much can it weigh? Okay, if it can only weigh this much because that's how much rocket fuel we have, or that's how much weight the parachutes can carry, then you got to make it lighter. How do you make it lighter? Well, the battery's got to be smaller. Lower performance motors, bigger blades, larger solar cell. That's how Ingenuity was decided to be this little tiny thing. Resources have to be shared, like data sensors, cameras, radios. When Ingenuity is using Perseverance as its buddy for all of its electronics and resources, Perseverance can't be doing a whole lot of science. And commands go out when they can. So on the next opportunity for Earth to communicate with Ingenuity by way of orbiters and Perseverance, that's when you send out the commands. Sometime later, they'll execute them. They'll give you a first heads up of, hey, I did it. It's successful. I didn't self-destruct, and you can still talk to me. And then later on, you'll get the bulk data sent back, and you can process it and produce things. So you start by sending confirmation that I've done it. You told me to do this. I did it. I'm still alive. And then the science data comes later over multiple passes, maybe. The best solution to improve this is, much like they're thinking of sending up a GPS and a data comms network for the moon, I think they need to start thinking about doing that for Mars as well. Once again, it's 1-800 Elon Musk. Just give him a call and say, can you put up a Starlink kind of thing around Mars?
Please.
But it only needs to be like equatorial orbital, geosynchronous. And geo is the wrong word because geo means Earth. It's Mars synchronous because of different orbital characteristics. But put one of those up, and now we can talk to anything on Mars anytime, because one satellite will talk to another satellite if it's not within line of sight within the Earth, just like Starlink does in Earth orbit. And in order to do all that back-end storage and processing, in order to avoid spending your tax dollars on ever newer, bigger, faster computers, we'll let the commercial sector do that for us, and we'll piggyback on it. So NASA uses storage farms and computing to process all the data, images, and video. And the other one you know, which is me. So, any comments or questions?
Oh, well done.
I know it's a lot of data, and I am recording this, so I plan on editing it, getting rid of all the faux pas, and then I'll put that up on YouTube. And once I have that, then I'll give people the link. I'll just say that I'm still in the process of editing last week's session, so it's going to take some time. There's just me, and I've been trying to create a startup company, so it takes time.
Good job. Very nice.
Yes, I enjoyed it.
Thanks,
So
Monroe.
much.
Okay. And
Thank you very much.
sure. So as I was saying, next week, you move some windows around because they move the windows around when you stop sharing. Next week, we'll talk about why we no longer have to think about contacting ET. It's gonna become, as the saying goes, axiomatic.
Okay, you gotta come talk to us.
What's the saying? Don't call us, we'll call you when we get damn good and ready. Hey.
Okay.
So was this far too detailed for people's tastes?
No, it was great.
No,
Okay, good,
no.
good, because that's the level I like to go to. If I look at something and I go, yeah, but what about, give me some details on that. If I find any tidbit fascinating, like, what's the northern gate of the Forbidden City called? It's the same name as the supercomputer in China. I'll throw those things in.